Thank you for joining me today. In this video, I will discuss the axial stress, axial deformation in composite members. Composite member or composite column is a member created from two different materials or more. Two different materials or more, maybe three, four, five, whatever. The most common composite members or composite column in construction is made with a combination of steel and concrete. But sometimes we can use timber, plastics, and the various other materials. But this is a common composite columns in our buildings, in our construction, is made from two materials, two main materials, concrete and steel. So if you look to this one, we have concrete and we have steel rebars, and sometimes we have steel member. All of them are embedded in concrete. Sometimes we have only concrete with steel rebars only. And the concrete cross section, sometimes it's a circular, it's a square, it's a rectangle, whatever the shape. But by the end, we have two materials creating your composite member. So what is the problem? The problem is we have a composite column with steel and concrete. In this case, we have a steel tube filled with concrete. That makes sense? And we have applied force, applied axial force. In this case, it's compression force, pushing the column. So what we need or what we are looking for how much axial deformation in this composite column, how much stresses in steel and stresses in concrete. How to solve this kind of problem, we need to understand what's going on. First of all, the two materials are sharing the applied load. What do you mean? I mean, the composite column is subjected to axial force P. Part of this axial force P will be supported by concrete, and this amount of force supported by concrete will be labeled by PC. The second part from the applied load will be supported by the second material, steel, will be labeled by PS. Keep in your mind, the applied force shared by the two materials. So I can say the part shared by concrete plus the part shared by steel will equal the original applied force. And this is equation number one. So first of all, the two materials are sharing the applied load. So the part shared by material 1 plus the part shared by material 2 will equal the total applied force. Keep in your mind, from mechanics of material, the part PC applied or supported by concrete will cause contraction in concrete, delta C. This delta C in concrete will equal P of concrete, L of concrete divided by A of concrete times E, the Young's modulus or modulus of elasticity of concrete. That makes sense? The part supported by steel will cause contraction, axial deformation in steel, delta S. This delta S will equal PL divided by AE for steel, P for steel, L for steel, E for steel, area for steel. But keep in your mind, composite material, or I'm sorry, composite column means the two material working together as one unit. So the composite column, the two material will extend or will contract equally as one unit. So the amount of contraction in concrete and the amount of contraction in steel must be equal. This is equation number 2 from compatibility equilibrium. Because the two materials are one unit working together as one unit. No one will leave the other one. No separation. If the concrete moved down 1 inch, the steel must move down 1 inch. If the concrete contracted 0.5 inch, the steel must contract the same amount. So the axial deformation in concrete must equal the axial deformation in steel. So PL divided by EA in concrete will equal PL divided by EA for steel. And this one will give you another equation. So if you solve the two equations together, you can find out how much is shared by concrete, how much is shared by steel. Once you get the value of these forces, I can say the stress in concrete equal the force in concrete divided by the area of concrete. The stress in steel equal the force in steel divided by the area of steel. Also, the final contraction in the composite column delta will be one of them, the contraction in concrete or the contraction of steel, one of them. Don't add both of them. No, one of them. The contraction in concrete, which is equal the contraction of steel, will equal the final contraction in the composite column. That makes sense? So we have two examples in this part. The first example, we have 8-inch diameter concrete. Column has 6 steel rebars embedded in concrete. So each rebar, the 6 rebar, has 0.5-inch diameter. So if you would like to figure out the area of steel, equal by divide 4 times 0.5 inch square. This is the area of one rebar. This one rebar has diameter equal 0.5 inch diameter. So the area of one rebar equal pi divide 4 times 0.5 inch square. Since we have 6 rebar, I'm gonna multiply it by 6. So the area of steel will equal by divide 4 times 0.5 square times 6. So it will be 1.178 inch square. What will be the area of concrete? The area of concrete, we have 8-inch diameter concrete column. So by divide 4 times 8-inch square, but don't forget to subtract the area of steel, because we already have these 6 rebars embedded in concrete, in this 8-inch diameter concrete. So when you are getting the area of the concrete, which is the area of the circle, I have to subtract the area of the steel rebars. So by divide 4 times 8 square minus 1.178, it will be 49.1 inch square. So this is the area of steel and this is the area of concrete. Keep in your mind this composite column under the effect of applied force P equal 30 kib. So I can say the steel will support a part PS. The concrete will support a part I'm sorry. PC, the amount shared by steel plus the amount shared by concrete will equal the applied force 30 kb. And this is equation number 1. The part supported by steel will cause delta steel. The part supported by the amount of force supported by concrete will cause delta concrete. Because the two materials are working together as one unit, so both of them will contract by the same amount. So the delta in steel must equal the delta in concrete. So the P, L, A, E of steel will equal the P, L, A, E of concrete. And this is equation number 2. Go ahead and put your numbers. Keep in your mind, the length of steel equal 3 feet. The length of concrete equal also 3 feet. So I can cancel each other. L, the length of steel, and the length of concrete. Both of them have the same length. The length of this rebar will be the same like the length of concrete. So I can say PS divided by area S, which is 1.178, time ES. I think the youngest modulus of steel is given 29,000. KSI. So this one in kib. This one is kib KSI. This one is inch square. We are good. Equal the part in concrete divided by area concrete 49.1 time E, youngest modulus of concrete, is given 4,200 KSI. I can simplify this equation. So I can say PS will equal, I think, .165 BC. What I did, I rearranged this equation and I found PS as a function of PC. So I can go back and remove PS and put 0.165 PC. This is the PS plus PC equal 30. The only unknown in this equation is PC. I can find it out. So it will be 25.7 kb. Go back to find out the value of the PS. It will be 4.3 kb. So the total applied force on this composite column is 30 kb. Part of this 30 kb will be supported by concrete. How much? 25.7 kb. The remaining part, 4.3 kb, will be supported by steel. So I wrote the equilibrium and the compatibility equation. This is the equilibrium, summation F of phi equals 0. This is the compatibility. I found out the internal forces in the concrete and the internal forces in steel. This is just a check answer, whatever. In kb. So the part supported by concrete equal 25.7. The part supported by steel is 4.3. What is the stresses in each part? So I can say stress in steel equal the amount of force supported by steel divided by area steel. So I will have 4.3 kb divided by the area of steel, which is 1.178 inch square. So the stress will be compression. Negative means compression because the applied force is compression. 4.3 divided by 1.178 equal 3.65 kb per inch square, which is called KSI. The stress in concrete equal the applied force on the concrete or the part of the force shared by concrete divided by area concrete. This amount of force equal 25.7 kb divided by area of concrete 49.1 inch square. So this stress will be compressive stress, 25.7 divided by 49.1. It will be 0.523 PSI. The final contraction in this composite column delta will be one of them, delta in the concrete or delta in steel. It's up to you. One of them. So let's take the PLAE for concrete. The applied force 25.7. The length equal 3 feet. I'm gonna multiply it by 12 to be in inch, and this one in kb. The cross-section area is 49.1. The Young's modulus of concrete is 4,200. Make sure the units are consistent. This one in inch square. This one is kb per inch square. So everything in inch, everything in kb, we are good. So 25.7 times 3 times 12 divided by 49.1 times 4,200. Your value will be 0.0045 inch. This is the total contraction or the final contraction in the composite column. We have one more example. For composite column, we have a concrete square cross-section reinforced by 8 rebars, and the diameter of each rebar is 1 inch. So the area of steel equal by divide 4 times 1 square. This is the area of 1 rebar. We have 8 rebars, so I'm gonna multiply it by 8. So the area of steel will be 6.3 inch square. And the area of concrete, we have a square cross section 15 by 15, so it will be 15 inch times 15 inch. Don't forget to subtract the area of steel because the steel rebars are embedded. So 15 times 15 minus 6.3, I got 218.7 inch square. The total applied force on this composite column equal to 150 kb. So I can say part of this force will be supported by concrete. The second part will be supported by steel. The summation of the two parts must equal to 150 kb. And this is equation number 1. The part supported by concrete will cause delta in concrete part. The part supported by steel will cause delta in the steel part. Since the two materials are working together as one unit, will move together, will deform together, so the contraction in concrete must equal the contraction in steel. So the PLAE of concrete must equal the PLAE in steel. Keep in your mind, the length of the concrete equal 3 feet. The length of steel equal also 3 feet. Both of them the same length, so I can cancel each other. So we have PC, I don't know how much. Area concrete is 218.7. Young's modulus of concrete is given 4,000 KSI. Equal PS, I don't know. Area steel 6.3 time E, youngest modulus of steel is given 29,000 KSI. So I can rearrange this equation to say the BC will equal 4.8 the BS. And this is equation number 2. So I can remove PC from this equation, put BC equal 4.8 PS. So the only unknown will be PS. I can figure it out, and then I can figure out the value of PC. So the part shared by steel will be 43.2 kip. And the part shared by concrete, it will be 207.3 kip. So I think we are missing just for approximation. That makes sense? So 43 plus 240, it will be 250. So 0.2 and 0.3 just approximation. That makes sense? So we can rearrange these numbers because I used approximation. So 43 and 207. That makes sense? It's not a big deal. So the part of a load supported by steel will be around 43 kip, and the part supported by concrete will be 207 kip. If you would like to figure out what is the stress in steel, equal the applied force in steel, the part supported by steel by area steel. So it will be 43 kip divided by the area of steel, which is 6.3 inches square. And this stress will be compressive stress. (6.82 KSI). Stress in concrete will equal the force supported by the part of concrete, PC, divided by area concrete. So this part is 207 kip divided by the area of concrete, which is 218.7. This stress will be compressive. 0.95 KSI. The final contraction in the composite column, will be one of them. The one happened in concrete or the one happened in steel. It's up to you. So let's do it PL divided by AE for concrete. P concrete, 207 kip. The length of the concrete, which is the length of the total the total height of the column, 3 feet. I'm gonna multiply it by 12 to convert it to inch. Area of concrete, 218.7. Youngest modulus of concrete is given by 4,000 KSI. Before finding the final answer, please make sure the units are consistent. This one in kip, this one in inch, this one in inch square, this one is kip per inch square. So we are good. So 207 times 3 times 12 divided by 218.7 times 4,000. The value will be 0.0085 inch. This is the final contraction, or the final the contraction in the column, in the composite column, which equal 0.0085 inch.